Millennia from now, when New York lies in ruin and Shanghai is but dust, this video will stand as a testament to humanity's former glory. In this chapter, we are going to work with the physical quantity that is energy. We have not discussed energy yet in this course. We talked about force, and when we defined force, we had a very specific notion of what is force. When we defined acceleration, we had a very specific definition of what is acceleration. And similarly for energy, we are going to have a specific definition of what we mean when we say the energy of an object. So, if we are working with energy, we could ask questions like energy, what is it? What is it used for? And why do we care in the first place? Well, the thing is, it is kind of tricky to define what is energy. Just like it's really tricky to define what is time, for example. And if you were to go to a very well established, brilliant researcher and ask what is energy, you probably still won't get a perfect definition. But if we study energy in the context of physics, we'll still be unable to define what energy really is at the end of this chapter, but we will be a little more aware of what we don't know. So, as a first definition, I propose that we'll describe energy as a scalar quantity that is related to the state of a system of one or more objects. So, let's unpack this definition that we are proposing. We say energy is a scalar quantity. That implies that energy is not a vector quantity. If I talk about the energy of a car, I'm not telling you what energy is yet, but you know right away that to describe the energy of that car, you only need one number because energy is a scalar quantity. Previously, when we talked about velocity and force, we often would break down these vector quantities into their components. We do not need to do that for energy. There's no such thing as the x component of energy and the y component of energy. Energy is just a scalar. You just need a single number to describe energy. We also say the energy is related to the state of a system. So, what do I mean by a system? What do I mean by the state of a system? Well, a system could basically be thought of as some physically possible scenario. So you could imagine a rock that is flying through the air with projectile motion. You could imagine a system as a chamber of gas molecules in a canister. You could imagine a system as a lot of dogs running around on a big farm. So, a system could be any physically possible setup that you could imagine. Now, what do we mean by the state of a system? I am going to propose that the state of a system is the pieces of information you need to answer a certain question. So, what do I mean by that? Let us consider the rock that is flying through the air example. Maybe I ask you a particular question, and to answer that question, you need to know the position of the rock. In that case, you would need three pieces of information to answer my question. You would need to know the position of the rock, which is basically saying you need to know X, Y, and Z, the location of the rock in 3 dimensions. In that scenario, I would say the state of a system that we are considering, the rock flying through the air, could be fully specified with three pieces of information: the position of the rock, X, Y, Z. Now, maybe I ask you a different question, and to answer that other question, you need to know both the position of the rock and the velocity of the rock. Well, now to fully describe the state of the system, to fully answer my question that involves the rock flying through the air, you need to now know 6 pieces of information. You need to know the position of the rock, which is X, Y, Z, and you need to know the velocity of the rock, which is Vx, Vy, Vz. So in that second question, you would need to know 6 pieces of information to describe the state of a system. So, in this way, the state of a system depends somewhat on the system in question and on the question that is being asked. For example, if the system is a whole lot of dogs running around in a big farm, and I ask you a question that where you need to know the positions of the dogs and the velocity of the dogs and the color of the collar that the dogs are wearing. Well, to fully answer that question, you would need to know X and Y and Z for the position of each dog. You would need to know Vx, Vy, Vz for the velocity of each dog. And you would need to give me the color of the dog's collar. So that would be 7 pieces of information per dog, and then multiply that by however many dogs are running around on the farm. So to describe the state of that system for that given question, you would need to tell me 7 times n pieces of information, where you have 3 pieces of information are the dog's position, 3 pieces of information are the velocity of the dog, 1 piece of information is the dog's collar, and then we assume there are n dogs running around on the farm. So the state of a system, I would say, is basically the amount of information necessary to answer a particular question. So the state of the system can change depending on which question is being asked. So if we're going to work with energy, what is energy? What is it used to accomplish? Well, you'll often see at the beginning of chapters, energy warms you on a cold day, makes roller coasters exciting, killed the dinosaurs, all that stuff. So I'm going to first propose, without defining energy, I am going to propose that there is a type of energy affiliated with motion, and I will call that kinetic energy. Now, think about what we're saying. We are just saying there is a scalar quantity, and that scalar quantity is related to the motion of an object. We are not saying anything more than this. So, presumably, if I have an object that is moving, that implies that object will have some amount of kinetic energy. Now, I don't know the equation for kinetic energy yet, but I could reason if an object is stationary, it will probably have no kinetic energy because it has no motion. And if an object is moving really fast, I expect that object to have a lot of kinetic energy because that object has a lot of motion in that moment. So, eventually we will define kinetic energy, but for now, this is all we're saying about kinetic energy. There is also a notion of potential energy, and potential energy is a scalar quantity related to the configuration of a system of multiple objects. Now, by that, I just mean the potential energy is related to where the objects are. So if I think of kinetic energy as an energy of motion, I could think of potential energy as an energy of position. Now, later on in this chapter, we will define what conservative forces are. For now, I'm going to tell you that the SI unit of energy is the joule. 1 joule is 1 kilogram meter squared per second squared. So before we actually talk about energy, we're first going to introduce the concept of work. Work is very closely related to energy. You could basically think of work as energy that is given to an object. Now, when I say energy is given to an object, I am implicitly saying that energy is taken from somewhere else and transferred to that object. So the energy comes from some external source. This energy is transferred to an object by a force acting on that object. Now, how could we visualize this? Imagine that there is a box sitting on the floor, and this box is just going to be stationary. I don't know much about kinetic energy right now, but we do know kinetic energy is an energy of motion, so because that box is just sitting on the floor being stationary, I could probably infer that that box will have no kinetic energy. Now, let's suppose sometime later I get that box to move. Now that this box is moving, this box will probably have some amount of kinetic energy. Now we could ask the question, if I want the box to move, how do I get the box to move? Well, the box was stationary on the floor. I push on it And as a result of me pushing on the box is now moving, the box now has some speed. So I could say that the box had no kinetic energy. When it was stationary, I gave the box a push, the box began moving, and later on, because the box is moving, I could say the box now has kinetic energy. So the act of me pushing on that box transferred energy to the box, transferred kinetic energy to the box. If you consider a sled that is initially at rest, and then a team of dogs pulls on the sled, well, the team of dogs are applying a force on the sled. As a result of the dogs applying a force on the sled begins to accelerate. It goes from rest to moving. The sled will have some amount of kinetic energy, the energy of motion. We could say that the external force, the dog's pull, caused the sled to gain kinetic energy. Formally, we would describe this as the dogs did work on the sled. The dogs gave energy to the sled. We will now formally define what we mean by work. So, to help us picture the concept of work, let's imagine there's a piece of cheese lying on the ground. We learned back in chapter 2 that displacement is a change in position vector. We didn't really work with displacement much yet in this course, but if I have a notion of the initial position of the cheese and if I have a notion of the final position of the cheese, I could talk about the change in the cheese's position, and that quantity will be a vector. The magnitude of displacement is how far it moves, and the direction of displacement is what direction the cheese moves in. So, how do we get cheese to actually move? Well, we have to pull on it. So let's imagine there's a goat, and that goat will have a rope in its mouth, and that goat is going to pull the cheese with the rope. In doing so, the goat is exerting a force on the cheese. Now notice that the direction of the force with which the goat is pulling on the cheese is different from the direction that the cheese moves. The direction of the force vector is different from the direction of the displacement vector. These two vectors are offset by an angle theta. Work is defined as the work due to a constant force causing an object to undergo displacement is given as Fd cosine theta. Now, work, we said previously, is the amount of kinetic energy gained by an object after it undergoes a displacement. So if I say the cheese begins over here and moves here after it undergoes that displacement, I could say by the time the cheese gets from here to here, it has gained this much kinetic energy. Within this equation, F is the magnitude of the force vector, D is the magnitude of the displacement vector. Now, if I stop and think about it, when I talk about the magnitude of vectors, I don't really need to think about their direction. I just need their total amount. So F is the total strength of the force, D is the total distance that the cheese has moved. However, I do need to account for the direction of force and the direction of displacement, in that force and displacement can have an angle between them. And this angle theta is the angle between the direction of the displacement and the direction of the force. If you think about it, this angle theta could be anything between 0 and 180 degrees. If force vector and displacement vector are parallel with each other, in other words, if they point in the same direction, theta will be 0. If force vector and displacement vector point in opposite directions, if they're anti-parallel, then this angle will be 180 degrees. And in general, this angle could be anything between 0 and 180 degrees. I said before that you could think of work as the energy that is given to an object from somewhere else. This energy is transferred to the object by a force acting on that object. So in this scenario, the goat does work on the cheese by pulling on it. So the goat transfers energy to the cheese by pulling on it. So I'm talking about what the cheese is doing, and external to the cheese is the goat and the force with which the goat pulls on the cheese. So, in a way, I could think of the energy as a noun and work as a verb. Energy is what is given to the cheese, and energy is given to the cheese by the act of the goat pulling on the cheese. Energy could be transferred to an object. When that occurs, the work will be a positive number. Work will be greater than zero with the equation we had on the previous slide. It is also to take energy away from an object. And when we calculate the work done in that scenario, we would get a negative number for the total amount of work done. To imagine what that might look like, think of a box that is sliding along the floor, and then you push on the box and eventually bring the box to a rest. Now, the box is not going to instantaneously come to a stop the moment you begin pushing. The box could be moving pretty fast. You push on it, the box will still slide, but it does take some amount of distance to slow down and come to a stop. So we could say, before you applied your push, the box was moving. It had some amount of kinetic energy. After the box came to a rest, it no longer had kinetic energy. So the box lost its kinetic energy as a result of you pushing on the box. In that scenario, if I were to calculate the work done on the box, I would get a negative number. So it's kind of like saying I gave negative kinetic energy to the box. Now, physically, that isn't really a meaningful concept. It would be more accurate to say I took away kinetic energy from that box. It also is possible to have multiple forces all acting on an object simultaneously. And some of these forces could be doing positive work, some of these forces could be doing negative work. It's also possible for an object to be doing zero work on an object. Within this goat and cheese example, we only considered the work done by the goat pulling on the cheese. But you know that gravity is also going to be at play. You know there's going to be a normal force on the cheese. Depending on how elaborate you want to make this scenario, there might be friction acting on the cheese. And all of these forces will do some amount of work. And within this, think about, is it possible for a force to do zero work on an object? And if I think about the goat pulling on the cheese, gravity pulling on the cheese, the normal force, friction acting on the cheese, of those four forces, think about it, which of those forces will do zero work on the cheese? Now, as I said, it is possible for more than one force to be acting on an object at the same time. And when that occurs, I could talk about the total work done on an object, or sometimes that's phrased as the net work done on an object. So let's say we have force F1, F2, F3 all acting on an object. I could say the total work done on the object is the work done by force 1 plus the work done by force 2 plus the work done by force 3. And I add up the contribution of the work done by all the forces acting on that object. Here, theta 1 is the angle between force 1 and displacement vector d. Theta 2 is the angle between force vector 2 and displacement vector d, and so on. Now, an object itself can only have one speed at a given time. Therefore, an object can only have one kinetic energy at any given time. And the total work done by all the forces acting on an object is the change in the object's kinetic energy. And this is known as the work kinetic energy theorem. This equation is going to be very useful in this chapter. We'll be seeing it a fair amount, and it could make some problems really easy to solve. Now, what are the forces acting on an object? Well, it could be anything. It depends on the particular scenario. You could be talking about the force of gravity, or the force of friction, or the spring force, or the electromagnetic force, or any other type of force you want. So, as an example, work or the lack thereof. One prank that astronomers like to do at the Anglo-Australian Observatory is they will wait for a night when someone is going to set up a camera and take a picture of star trails. So what you do is you open the shutter of a camera, you leave that shutter of the camera open for something like 6 or 8 hours, and as the Earth rotates, the camera is stationary relative to the observatory dome, but the Earth is rotating and it will appear as though all the stars are rotating in the sky. So if somebody finds out one astronomer is setting up this camera to take a picture of star trails, another naughty astronomer might run up to this observatory dome with a flashlight and write some dirty words to be developed in the picture later. So we could ask the question, what work is involved in this prank? Well, let's imagine the astronomer is initially at some position over here, and then the astronomer runs up a ladder and runs across a catwalk. The astronomer could take out a flashlight and drop some F-bombs, write words like fart with the flashlight. And then the astronomer will run across the catwalk, run down the ladder, and end up at this position here. So if we ask what work is involved in this prank, well, in this scenario, the initial and final position of the naughty astronomer are the same. And that implies the displacement of this astronomer is going to be 0. If the displacement is 0, that implies the work is 0. And therefore, we may conclude that there was no work done at the Anglo-Australian Observatory that night. And if you are curious, this is actually a real story. My source for this was a dude who actually worked here.